Okay, so today we're going to talk about three trends and how they fit together and how they don't fit together. So you should have a staple pack of lecture notes that says atomic interactions and definitions. It would behoove you to have that out so you can play along as we talk about this. And they're all related, but they're all kind of different. So,
Oh, wow.
what?
She's been, oh, my periodic table.
Oh, wow. Yeah.
That was the reaction I had. Oh, wow.
That's,
It's been a tough year for me.
I get
It's
that.
only been a semester. This has been the longest semester of my life.
Okay. Got it.
Well,
All right.
with the current.
So let's talk about these like different things. So let's talk electronegativity. These are, like I said, those are all related, but they're kind of not. So if you look on the back chart, back side of the book, there's this periodic table.
No, there isn't.
There should be.
What? Well, there's that.
Oh, it's this one, it's this one, it's
You're a
this one.
lying liar who lies.
Which one?
Atomic interactions and definitions.
Yeah.
There's not something on the back side.
Yeah, it's on the second page.
What's on this?
This is all we have.
Is it colorful?
Oh, this is the
Mine's-
periodic,
yeah, this is all we
have.
Would you like to look yourself?
That's so weird.
It's so weird.
Okay, all right, we're just gonna wing it.
Oh, okay.
Okay.
That's
Okay.
Now we're talking.
That's so weird that the first 3 pages printed out, but the first page didn't. Okay, so,
Technology.
I know. All right, so electronegativity, historically, this came out to be in the 1930s, mainly because of the fact that they had to wait until they figured out that there were actually electrons and protons and how things bonded together. So when you look at electronegativity, basically, it's the simplest way to think of it is that how willing an atom is to take away electrons from something else, okay? And electron affinity is kind of like how willing is it to hold on to its own electrons. It's a short version. So if you look on a trend, so let me draw what you should have had on that fourth page. I'll get that fourth page for you tomorrow, okay? So you have general trends. And so if you look on like that first row of columns, okay, the alkali metals, those all have a value of about 0.8, and this, it's a number that doesn't mean anything. It's a relative value, okay? And technically, these are named in Pauling's, named after Linus Pauling, who was the first physicist, chemist who really came up with a way to measure this. And again, just the measuring process is difficult. Because, like, how do you measure quantitatively the ability of an atom to take in electrons from something else? So here's the analogy that I would give. So let's say that we're going to play a game, and if you win, you have 8 game pieces. Okay, so 8 game pieces is the magic number. Okay? So Charles has 1 game piece, okay, of the 8. You just have 1. Okay? Bethany has 7, and Gap Sean has 8. Okay? So you've won. You have all 8 game pieces. Bethany's close, she has 7. Charles has 1, he's just started on the game piece, okay? So, of the 3, because you've won, of the 3, who's gonna have the greatest willingness to hold on to their game pieces?
Bethany.
No.
Gershon.
Sean is, because he's won, okay? He has all 8 game pieces. Now, is Gap Sean going to be willing to take in game pieces from Green? Why not? He's not going to. Why? He has the 8 game pieces. So Gap Sean is like the noble gases, okay? So the noble gas is way out here, on terms of electronegativity, they don't have any. Mainly because of the fact that with electronegativity, and it's the willingness to bond with other atoms and take in their electrons, Shaw's going, basically, I don't need anybody else. I've won. I don't need anything. Now, what about Bethany? Would she be willing to take in another game piece?
Yes.
Absolutely. Why? Yeah, she has 7. She only needs 1 more. So she'd be like, hey, Jade, give me that game piece. Okay? Now, especially with Charles, because Charles is going to be over here going, man, I only have 1. Charles is going, I'll give you the 1 game piece, but now we kind of have to share the winnings, okay? Because everybody's going to be more stable, because you're going to have the 1, you're going to win, okay? Stay with the story, Charles, my story, okay?
Okay.
And so then you guys are going to become more stable, because Charles is stressed because he's over there going, man, I only have 1 game piece. This is bad, okay? Bethany's going, come on, I only need 1 more, okay? All right? So those two could form a coalition. So Charles is over here, and he's like lithium, sodium, potassium, okay? So he's like the alkali metals. He has the 1 game piece. Now, he might be willing to take in a game piece. So like, if Kevin walks up to him and goes, hey, Charles, I got a game piece. Charles goes, I'll take it, okay? Maybe it isn't like, yeah, wow, I really, really want one. Versus if Kevin goes to Bethany, and Bethany, you want a game piece? Bethany's going, oh yeah, okay? Because she has 7. So she's really going to take that in. Gap Sean, if Kevin goes up to Gap Sean's going to know I'm good. Thanks. Okay? Don't need it. I'm good. So if you look over here on that last group, not the noble gases, okay? So there's the noble gases. So what's the column just to the left of the noble gases? Halogens, right? So Bethany is like the halogens, okay? They have an extremely high electronegativity because of the fact that they are very, 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 very willing to take in those electrons because they have 7 game pieces. If they can get 1 more, they can be like the noble gases. So on a relative value, like fluorine has a value of 3.98, and we'll talk about this trend. Chlorine is 3.16. Bromine, this would be so much easier if you guys had this, 2.96, and iodine is 2.66. Okay, so why do you think fluorine, of all of the halogens, has the highest electronegativity?
Because those electrons are the closest to the nucleus.
Beautiful, okay? So if you look at fluorine being on that second row going across, fluorine is just filling out the second energy level. So here's the nucleus, right? And there's like 1s, looks like helium. And in that second sublevel, there are a total of 7. So Bethany is trying to fill a game piece that's right there close to her. Okay? So an electron goes by, or a game piece is going to go by, and Bethany's going to go, whoop, that's mine. Okay? She's going to be really, really willing to take that in. Okay? Now, we have Morgan. Morgan also has 7 game pieces. Her game pieces are far away from her. She still needs 1 game piece, but they are farther away. So as you increase that distance, that willingness to take in a game piece decreases. She still wants to take in a game piece, but it's kind of far away. It's like, is it worth the effort? Yeah, maybe, not so much, maybe. Whereas Bethany's going, that's close to me, I'm really, really, really going to take that in. So here's your general, this is a general trend. general trend. As you go across, electronegativity increases, okay? Because as you go across, you are in effect gaining gain pieces, okay? So if you look at oxygen, fluorine, and go across. So oxygen is going, if you look at oxygens and you compare that to fluorines, oxygen is 3.44. So that would be like Jaden, because oxygen has 6 valence electrons. So Jaden's sitting there going, I need 2 gain pieces, right? So she is willing to take in gain pieces, just not quite as strong as Bethany is. Because Bethany's filling, she has 7. She only needs 1. Jaden is like, I'll take 2, okay? She's willing to take one in, but it's like, Jaden might go, that's a little bit more effort, because they have to take in 2. Don't know, maybe yes, okay? And then you get carbon, for example. So carbon's value is 2.55. So carbon is 2.55. So that would be like Cohen having 4, okay? It's like, it's a lot of effort. So carbon can kind of go either way. So carbon kind of has a split personality when it goes to its electrons. It has 4. It's like, do I lose the 4 electrons and look like helium, or do I gain 4 electrons and look like neon? Don't know.
Whatever's
Okay?
easier.
Don't know what to do, because there's 4. So what carbon does typically then is that carbon shares electrons, okay? And this is why carbon hybridizes, because of the fact that it really doesn't have a high enough electronegativity to really take electrons, because it's like it has 4, it's like, God, that's a lot of effort, I don't know what to do. Bethany, though, sits there and goes, score, I know exactly what I'm going to do. Sean goes, not so much, okay? So, when you talk about electronegativity, the higher the electronegativity value is, the more willing it is to form bonds with other atoms. Yes, Cohen?
This is a real question. You said that the electronegativity and the is like a general trend.
Yes.
So there are exceptions to that rule?
But generally not. I mean, it's, so like if you look at, let's say for example, going across, there's some weird anomalies like silver, which is right to the right of cadmium, has a slightly lower value, but not much. So there are some minor exceptions to this, but as an overall general trend.
How does that work?
It has to do with like it happens when you get into the really big electron clouds. With the simpler ones, the trend holds. It's those transition metals in the middle, which is tough to say. That gets a little bit wonky because you're filling those D sublevels and those D sublevels. But the overall general trend would definitely is, as you go across, it gets bigger. And as you go down, it gets smaller. That's really what you need to know. Don't worry about the exceptionalities. Okay, so that's your electronegativity. Now, you guys have, which follows the kind of the same thing, you have this chart of, you do have the electron affinity chart, right? Okay, there you go. So electron affinity and electronegativity are somewhat similar. But here's what's the difference. With electron affinity, that is more of a technical definition, so there's kind of 2 criteria that have to be met. One, you have to have the material in the gaseous phase, which for gases isn't a big deal. Problem is that you get into metals, like how do you make lithium into a gas? Well, you got to boil it and then you have lithium gas. So just physically, that's difficult to do. So there's a lot of, so when you look at the chart that you have, notice that there's kind of like, there's this kind of big gap in the middle. So you really don't know what we got going on because it's just kind of weird. So, but again, you can look at general trends. So here's the first criteria, is that it has to be in the gaseous phase. The other thing that happens is that it's the energy that is either released or absorbed, endothermic or exothermic, when an electron is added to that single atom, okay? So on the front, it's got this example, if you look at those lecture notes. So down there at the bottom, it's got fluorine as a gas, and what's going to happen here is that if you take away an electron, okay, and that has to do with ionization energy, but we'll get, because that's like the other side of it. So ionization energy is the opposite of electron affinity. So electron affinity is the amount of energy that's going to happen if you make it take an electron. So, or a game piece, if you go with the game piece analogy. So if you look on that far right side on the noble gases, helium, neon, argon, okay, you'll notice with those that they don't have an electron affinity value because it's the same thing. Gap-Shawn being a noble gas, someone comes up to it and goes, "Excuse me, sir, can I offer you an electron or a game piece?" And Gap-Shawn, being the noble gas that he is, goes, "Away with you, peasant," okay? He doesn't care. There's no energy involved with Gap-Shawn getting a game piece because he's nobility, and it was like, whatever, go away, peasant, okay? Now, Bethany, though, someone walks up to her and goes, "Hey, Bethany," there's a game piece. Bethany's gonna go, "Score!" Because now she's gonna get very excited because of the fact that she has now all 8 game pieces and she's gonna win. So she is gonna have a much more energetic existence or experience when someone gives her a game piece, and Gap-Shawn's gonna be like, "Whatever," okay? Nothing, it won't phase Gap-Shawn. Bethany is gonna go, "Score!" Okay? Now, Charles, it's gotta be a little bit different. He might get a little bit excited going, "Okay, hey, all right, great, gave me a game piece, whatever," okay? He'll acknowledge it. "Hey, I'm on my way," really doesn't make that big a difference. So in all 3 situations, you're going to be given a game piece. Charles is going to be like, "Okay, thanks." A little bit excited, but not much, or as excited as Charles can be. Bethany is going to go, "Score!" Because now she has all 8 game pieces, and she's going to look like a noble gas. And Gap-Shawn's going to be going, "Away with you, peasant, I don't care." Okay? See the difference between the 3. So, electron affinity has to deal with energy of a single atom in terms of gaining an electron. Electronegativity is an atom that exists typically within like a molecule, and it's willing to take electrons from something else. So you can think of electronegativity as being like the willingness to go and steal an electron, okay? Bethany, probably given the opportunity, as nice as she is, she would steal an electron or a game piece from Jaden at the drop of a hat, okay? Because she has 7 game pieces. But then she'd form a bond. She doesn't like she's not going to leave, Jaden hanging. She'd, "Hey, I showed you game pieces. Let's have we'll win, okay? We'll share the prize money, okay?" And Gap-Shawn is going, "It's not worth the effort for me to take a game piece because I don't care, because I have 8 game pieces." Okay, so you see this idea. Now, here's the last one. This is where this hopefully all fits together. And this is what's known as first ionization energy. What?
Can you explain why the electron affinity for nitrogen is negative?
Okay, because some of them are negative because if they do gain an electron, they actually lose energy or gain energy. So with nitrogen, and that's what I said, this is general trend. So if you look on that as you go across, the general trend is that the electron affinity is getting bigger, okay, as a general trend. Very rarely do you have a negative value, which means that would be like me giving a game piece to nitrogen, and nitrogen goes, "Man, I really don't want this," okay? That's the short version. Whereas everybody else gets excited and goes, hey, I win. Kevin?
Okay, so hold on. If electron affinity is a measure of energy and nitrogen's negative, does that mean you have to put energy in to force it to take the
Basically,
electron?
yes. Because it doesn't want it. So that would be like Haley's sitting there going, man, I'll take a game piece, but you gotta force me to take it. Okay? Whereas everybody else is like, oh, I get more game pieces. So that's why I said these are like broad general trends. Okay. Now, first ionization energy. Imagine that I'm going to go up to the three players, Charles, Bethany, and Gapshon. And I'm going to take away a game piece from each one of them. Okay? So first ionization energy would basically be how hard do I have to fight each person to take away a game piece. Okay? Now, up to this point, Gapshon has been nobility. He hasn't cared because it's dealing with gaining electrons from something else. Gapshon hasn't cared because he has all his game pieces. Okay? Charles has been kind of indifferent. Bethany's like, oh, I want a game piece. Now, I'm going to go up, and I'm going to take away a game piece from either Gapshon, from Bethany, or Charles. From my perspective, who's going to fight me the least?
Charles.
Why you, Charles?
Because I don't care.
Yeah, he might fight me a little bit. It's like, dude, I only have one. Okay? Don't take that away from me. But that would probably be the extent of it. Okay? He might put up a token, bit of effort going, come on, Burkamp. I only have one. Don't take it away. Okay? But that would be about it. Now, Bethany, what about Bethany?
Fight.
Throw hands.
We're gonna have to throw hands.
Let's see it happen.
No.
Oh, man.
I lose. This isn't fair.
Okay.
I'd like to see that.
I just like to put my hand on my shoulder. So, let's just say. So, now, Bethany is going to fight me. Why?
She's only one away from.
She's only one away. It's like, Burkamp, come on. I'm only one away. Okay? So she's going to fight me much more than Charles is. Now, then there's Gapshon. Now, is Gapshon going to fight me?
Yes.
Absolutely. Now Gapshon's part of the story. Why?
Has all
He
this.
won.
He is the winning combination. So Gapshon's going to go, bring it, Burkamp. Come on, old man. I'll fight you. Okay? He's going to be all like, come on, man. Come on. Okay?
That's good. I like that. I tell you to get into a lot of fights.
Oh, yeah. That's what I do on the weekends.
Yeah, I know.
Burkamp,
Fighting.
Burkamp Fight Club.
Yes. We should
Yeah,
call that.
BFC. There you go.
No one talks about it.
So,
I'll put money on
Yeah.
there you go.
ATM.
Don't. Oh, you're going to lose. Not necessarily. Guy. Now, why is Gapshon going to take the most energy? He has all 8 game pieces. He has one. If I take that game piece away, then he's going to be like the other peasants. It's like, oh man, I'm losing my nobility status. So if you look at that trend, okay, and it's got the first ionization energy, like lithium is like 520. You go over there to neon and it's like 2080, okay? That's like a 4-time increase, okay? So now, the noble gases, this is the only time the noble gases are part of the story. Prior to this, they haven't mattered. So there's a couple of trends, though, if you look at this. If you look at, like, lithium, sodium, potassium, if you go down that column, even within the alkali metals, what happens to the first ionization energy? It gets less. Why? Yeah. So if Charles is lithium and he has that one game piece and it's right there beside him, he's going to like, okay, he's going to put up a little bit of token resistance. Now, if Graham has one game piece, but that one game piece is backed by the roller coaster, and if I go to take it, Graham's going to be like, whatever. He might wave at me when I go by. That would be the extent of it, because of the fact that it's so far away. So this is, again, there's this inverse relationship between forces and distance. You increase the distance, you decrease the attractive force. You look at Bethany. So Bethany is going to be like fluorine. Okay, so if you notice that fluorine has a very, very high, relatively speaking, on your halogens, that's 1681, chlorine is 1250. So if fluorine is representative of Bethany, why would you have a very, very high first ionization energy?
Because I don't wanna give away my.
That's part of it, but where are your electrons? If you're fluorine, are your electrons in the first energy level or the second energy level?
Second?
Second, because you're in the second column down on the periodic table. So your 7 electrons are in the second energy level. That's pretty close. Now, if Jaden is chlorine, you're also going to have 7 game pieces, but your energy level is in the third. So that's a little bit farther away. So they have that in common, that they both have 7 game pieces. But Bethany is filling out the second energy level. Jaden's filling out the third energy level. So they both want to hold on to it, but Jaden won't be able to hold on to it quite as strongly because she's filling out that third energy level. Now, you look at the first ionization energy. You look at helium versus neon. What do you notice about the first ionization energy of helium?
Super high.
Super high. It is super high. Now, and here's the reason why. It's you're filling out the first energy level that's closest to the nucleus, okay, and it's stable. So this is why it is exceptionally difficult to get helium to react with anything. Now, you compare helium to, let's say, fluorine, okay? Fluorine has 7 valence electrons. That would be like Bethany. Hey, I got 7, I need 1 more, okay? So imagine, if you will, there's a party, and there's a big party. And you have all these different chemicals interacting at this party, okay? So Bethany was going to be very interactive at the party because she needs 1 more game piece. So she's going to come up, hey, spare game piece. How you doing? Yeah, game piece, thanks. We'll form a bond. Okay, we'll split it. Okay, so Bethany is going to be very reactive. Charles is going to be willing to react with Bethany because he has the 1 game piece. He gives that to Bethany. They now form a bond. Cool. Okay? Because they're a bond between them. Gap-Sean, how would Gap-Sean act at the party? Yeah, Gap-Sean's like, don't talk to me. Go away. Okay? He would be like the ultimate party snob. Okay? It's like, I'm here, that's enough. Don't talk to me. Okay? I've made an appearance, leave me alone. Because he doesn't need any game pieces. So Gap-Sean would be this snobby little thing. Now, let's say, for example, we talked about what we talked about yesterday, and you get into carbon. So carbon wants to make methane. Okay? So you got CH4. So carbon, 1 carbon atom, isn't going to form a stable bond with just 1 hydrogen atom. So because carbon is covalent, carbon has 4 game pieces. He needs 8. So even if he comes up to another hydrogen, okay, now he's just up to 5. Oh, hey, let's react with the second hydrogen. Okay, now we're up to 6. You got another one, 7. You got a 4th one. Oh, now we're up to 8. So if Cohen being carbon, then Cohen would need to form bonds with 8 people. Whereas Bethany, only having 1, needs 1. Now, here's an interesting thing. let's say carbon, carbon, is sitting here with 4 valence electrons. Bethany comes up, looking like fluorine, and she has 7. So, if Cohen is going to form a bond with Bethany, do you think that would just be in a 1-to-1 ratio?
No,
No, why not?
because I still got 3 leftover pieces.
Yeah, so you might come in here and go, oh, hey, are there some more Bethanys around? Not that you're not unique, you are. So, if that's the case, guess what? You're gonna make CF4, otherwise known as carbon tetrafluoride, okay? Because of the fact that those fluorines are going to need, each is going to need an electron. Now, what type of hybridization is carbon going to undergo?
SP3.
SP3, because of the fact that you're going to form, you need single unbound electrons. Are CH or CF4 going to form any pi bonds?
No.
Why can it not form a pi bond? Yeah, there's no non-hybridized p orbitals to form a double bond. So you know all of these are just going to be existing as single bonds, as sigma bonds. Got the idea? Okay. So I don't know why that last page didn't show up because it's on mine. So I'll get you that last chart. So here's, I'm not going to expect you to know a whole lot, but there is one thing, and I'll get you those numbers on that electronegativity difference. Basically, if there's a big difference between your electronegativities, and here's the quintessential example. If you look at the extremes, like between your halogens and your alkali metals, if there's a big difference in those electronegativities, you form ionic bonds. If there's a small difference between their electronegativities, like carbon and fluorine, you tend to form covalent bonds, okay? Because covalent bonds, basically, Cohen goes, hey, I've got 4, I really don't have enough moxie to form, really pull those electrons away, so Cohen's willing to form a communal thing. Because now, with Bethany and Charles, though, Bethany's going, wow, I really need that electron. So Charles is going to go, hey, this is on you. You take the electron, just give me some of the money. I really don't want the electron. So Bethany and Charles would form an ionic bond because there's a huge difference between those electronegativities. Whereas with Cohen and Bethany, they're very close together on the periodic table, especially nonmetals. So those tend to form covalent bonds because of the fact that their electronegativities are pretty close together. Okay, stand up, take a quick stretch. I gotta go over one other thing and then we'll be good. And yes, you are gonna have a simple assignment tonight.
How long is it?
It's not bad.
Are you ready, Charles?
Whether
Whether this is an above average AP physics class at all.
Because I am.
Hey, Berg, do you want an orange?
No, I'm fine, thank you.
That will make up for your GPA.
That orange is a lot bigger than the other one.
Yeah, this one's from my house.
Oh my god, it's still like.
Take a guess.
I was gonna tell you.
Did you say lime?
I was gonna say something fast, I think that was.
Bro.
Still like.
Oranges are
Wow.
they're 3 now.
I really captured that. This is all.
You guys surrounded it. Shut up. Why is everyone surrounded?
As bird? Yeah. Did you have
I guess I should say that.
not burnt.
Wait,
I literally told
No, this is me.
Yes.
That's you when your glasses are like in front of your face, like it's really small.
This is me.
I work on it and I got scared. Yeah, I'm not Grom.
Let's see, one hand drop.
You know what?
There's a tiger at the Southern County Zoo named Grom.
There's 2 tigers. There's Grom.
And it looks like Callisto or something.
Yeah.
which is weird names for type.
Yeah, but like Grom, weirder. For
Huh?
Because Grom was a guy and Melissa was a girl.
Weird to not
So like the girl got a really pretty name and then Grom.
Yeah, that's weird.
And Eddie keeps calling me Grom.
Hey, you love it, like,
I didn't know. When
Everyone said, me Grom, me clean.
yes, because in the moment he was speaking for Grom. Because he can't do it himself. Because he's a tiger.
I tried to draw Plankton, but I forgot.
That he was in blue on the outside.
And I covered over his mouth.
Criminal. Get on your nose. It's like barbecue snow. Barbecue never
Gargoyle?
What? He does 4 feet.
And wings. And orange. And his ankles. This is my bird. Mostly. And I have Sydney. My other bird.
I love Brian. Not a bad one.
Not bad.
I saw him
I have I just haven't done
Bird.
68.
What?
Is this really good?
425.
What do you mean?
Is it syrup? Would you like put something that's not syrup in the
Hypothetical,
bottle?
could I?
I used it earlier in the week on some pancakes.
Why wouldn't it
Did
be
you bring
syrup?
pancakes from home or did you
I've
make
never
them?
tried syrup.
My first thought was that you made them here and I was like, it was like a Munch
He got,
burner.
yeah.
Munch burner and a
Get a hot plate, thank you very much.
Yeah, I take a hot.
Yeah.
pancake batter.
Yeah, but he didn't say that.
Were they,
You implied it.
batter or
Yeah.
I thought they
And we'll mind
No, I
it.
cooked them like, it was like Monday, I cooked them.
I'm not trying to.
They said the same thing.
You're gonna have to come back over here though, physics. Yeah,
You just sit next to just flip and play with that.
Or we know that's not.
Alright, well, I never stopped the camera, so that's on YouTube.
Are you afraid?
I said him down way too long.
Talking about.
I am poisoned.
Exactly what I'm.
Him down.
I'm dead. I'm poisoned. The drink, the drink. Yes, I do.
I'm not calling mom.
There's neutral.
I'll be the orange, I'll go eat the tiger. This will be my best work.
No, that's oxygen this weekend.
That's Actually, I was mostly nitrogen.
I have like 5 pieces of paper left for the rest of the year.
Okay,
Oh, you're out of time.
are we still going?
Yeah.
Okay.
It hurt all that.
All right, so it's rare that they ask this on the AP exam, but I just want you to kind of be aware of it in case they do. And it's a weird kind of wonky formula. It's this concept of formal charge. Literally about every 3 or 4 years, they'll throw in this concept of formal charge. It's not used very often, but it's just so that if you see it, you're not gonna flip out. Okay?
Are we about due for one?
Kinda, yeah.
Oh, man.
So, but they're also shifting to this online format, so God knows what they're gonna do. So I think all of the rules are out behind it. Okay, so here's how you calculate formal charge. It's somewhat similar to what we talked about yesterday in terms of like how many you need minus how many you actually have, and you get the number of shares. So to get formal charge, and your formal charge is either gonna be like a positive, it's gonna be a small number, okay? Typically it's like 0 or 1, and sometimes -1. So here's kind of your formula, and this is why it annoys me when they put this on there, because it's such an obscure thing that you have to keep track of. So basically, you take the number of, here's like the formal equation. And no, on the test, I'm never going to expect you to actually be able to calculate formal charge, but I'm going to expect you to kind of know, like, here's the big picture of it. So more 2 examples, you can kind of see the difference between the two. So you take the number of valence electrons minus half the number of bonding electrons minus the number of non-bonding electrons, and then you get a number, okay? So what I have here is like fulvic acid. So just worry about the structure, and they would actually have to give you the structure to know this. So let's start with this. You have carbon, and then you have a triple bond between the carbon and the nitrogen. So even if you focus on that carbon, what type of hybridization has the carbon undergone?
SP.
What did you say, Charles?
I didn't say anything. SB.
You're like praying.
I realized something.
Is it a good something or a bad
It's
something?
bad something.
You said SP3, didn't you?
No.
Oh, I thought you did.
That was me. I said it.
Oh, you said
That is
SP3.
me.
Okay.
I just counted the lines and
And
everything.
that's why I said you can't count the number of
I
lines.
know that
Me
now.
and Frozen.
I corrected myself. Thank you very much.
So, look, for carbon to make a triple bond, what do you have to have?
2
non-hybridized p orbitals. Can you make a triple bond with sp3 hybridization? No. Why? Because if you have sp3 hybridization, everything is screwed up. Okay, you have no non-hybridized p orbitals. So the carbon is going to undergo sp hybridization because it's going to screw up one of the s's, one of the p's, and then it's going to leave 2 of those p orbitals non-hybridized to form a bond. Okay? Makes sense. So the first thing I'm going to do is count the number of valence electrons. Now, I'm not going to worry about the hydrogen because the hydrogen only has the 1 electron. Typically, what you worry about are the ones that are going to change. So, and this is going to be the second structure that we're going to look at, which is going to be the only difference is that we shift a bond from a triple bond with the carbon and nitrogen. We make that a double bond, and then we put that second bond over there. So the other thing, I'm not going to worry about nitrogen. And the reason I'm not going to worry about nitrogen is because if you look at both of those structures, nitrogen on both of them has a total of 4 bonds. It's just where you distribute the bonds. Carbon, though, fundamentally changes because on carbon up there, carbon has a total of 4 bonds, whereas down here, carbon has a total of 3 bonds. Over there, with that oxygen up there, that has a single bond with the nitrogen, and the oxygen changes, and it has a double bond down here. So what I'm going to look at is a comparison to see, okay, how does the carbon and oxygen change from that top structure down here to the bottom structure? Hydrogen and nitrogen are there. I just don't worry about them because nothing changes in the total number of bonds with those atoms. I change the total number of bonds with the carbon and the oxygen, okay? So typically when you look at formal charge, how this plays out, typically you're given 2 different structures and you say which one is going to be most likely to happen. So the only way, one method is that you look at the formal charge. And so what should happen, and this will make sense in just a second, the more stable structure is the atom that has the highest electronegativity. This is why I had to talk about electronegativity before I talk about formal charge. So if you're comparing carbon and oxygen, which one has the higher electronegativity? Basically, is it Cohen or is it Jaden?
Oxygen.
Oxygen does. Why?
Because it's farther right, so it's
Yeah,
got more.
it has 6 game pieces. Cohen only has 4, right? So oxygen has the higher electronegativity. So when you're comparing these structures, and this is what you'll see the math in just a second. So the structure that's going to be most likely to happen is the one where oxygen has the more negative formal charge. Okay? So it's just like, okay, what can we compare these to? This is the method. All right. So if you look at this structure, here's what I've got. So the first thing you have to have is the number of valence electrons. That's just straight off the periodic table. It's Cohen. He has 4 valence electrons, okay? What we do with it, bond it, whatever, that doesn't change. Same thing with oxygen. Oxygen is going to have 6. Straight off the periodic table. Count the number of dots. That's all you have to do. The tricky one comes when you have half the number of bonding electrons. So if you look at carbon, and remember there's always going to be, the reason that you divide by 2, it's kind of like what you did yesterday when we were trying to find the number of like shared electrons. We found the difference and we divided by 2 because there's 2 electrons involved in forming a bond. So if you look at carbon, this is the total number of electrons that are involved in forming the bonds with carbon. So you've got 1, 2, 3, 4. You've got 4 bonds. Each one of those involves 2 electrons. So that's why this is going to be half of 8. Okay? Does that make sense? Yes?
Why can't you just count the number of bonds?
Well, I'm just telling you this is the technical way of calculating. I'm just telling you this is the technical way of calculating the formal charge.
Okay.
Okay? So if you see it, yes, you could just count the number of bonds. I agree. But this is when you look at how it is written out in the formal literature, this is how it's done. Okay? You're right, it would be simple, but that's not what we're going to do.
Okay, cool.
Hey, sometimes science just gets a little bit wonky. Okay, now, then you have subtract out, the last thing is the number of non-bonding electrons, otherwise known as like the unbound electron pairs. So carbon doesn't have any. Okay, so carbon has all of its electrons are tied up forming bonds. Okay, so I take 4 minus 0, I get 0. So the formal charge on the carbon atom is 0. Okay, it has no meaning because it's just going to make a comparison. All you need to know, hey, that has a value of 0. Now, if you go through the same process with oxygen, again, I'm not going to worry about the nitrogen. It's there, but nothing changes. So I'm just going to worry about the oxygen.